Hello everyone, welcome to this lecture. So far in the earlier lectures on rotational spectroscopy, we have only considered the energies of different rotational levels. We saw that the energy is given by B times j times j plus 1. So, this is the energy nu bar j in wave numbers. So, that is the energy depends on only one quantum number j, that is the rotational quantum number. We also focused on the energies of the lines in the rotational spectrum, and these energies of the lines are given by 2b times j plus 1 for a transition from j to j plus 1. However, we have not focused on the relative intensities of these spectral lines. The intensity depends on population, and population in turn depends on Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution. So, the Maxwell-Boltzmann distribution is given by this equation. So, we see the population of any level, if we compare with the population with some other level, this Maxwell-Boltzmann distribution depends on the energy gap between the two levels. But additionally, it also depends on the degeneracy of the energy levels. So, we can write another term here, which is G j, where G j is the degeneracy of the jth level. So, there may be a number of rotational states corresponding to a given rotational energy level. In other words, for a rotational level, there may be degenerate rotational states or states with the same energy. So, in order to understand the intensity of the rotational spectral lines, we need to work out what the degeneracy is for each of the rotational energy levels. As we have already discussed, the rotational energy states of molecules are related to its rotational angular momentum L, and the relation is given by E j equals L squared by 2 I, where L equals root over j times j plus 1 h cross. As angular momentum or L is quantized in units of h cross or h by 2 pi. So, we can write L equals root over j times j plus 1 units. Angular momentum, being a vector, has both magnitude and direction. The direction of the angular momentum is along the axis about which the rotation occurs, and is generally drawn as an arrow of length proportional to the magnitude of the angular momentum. So, here we have a diatomic molecule. So, here what we can see, this red arrow is the axis of rotation around the center of mass. Now, we can see from this arrow that this diatomic molecule is rotating anticlockwise. This yellow or orange arrow shows the angular momentum vector. So, this is the magnitude of angular momentum, and this direction is the direction of the angular momentum. So, the direction of the angular momentum is given by the right hand rule. That means, if you take your right hand and if these 4 fingers point into the direction of rotation. So, I am talking about an anti-clockwise rotation. The direction where your thumb points, that is upward direction, is the direction of the angular momentum vector. So, you can see, because in this case the rotation is anti-clockwise, the angular momentum vector points upwards. On the other hand, if the rotation is clockwise, then we have to put our hand like this. When these 4 fingers points at a clockwise direction of rotation, and you can see the angular momentum vector in this case will point downwards. So, now let us discuss the orientation of the angular momentum vector in space. So far, from quantum mechanics, we know the magnitude of the vector, but now we want to know about the direction. Say we have got an arbitrary laboratory fixed axis, this is the z axis. Now, let us draw or have this diatomic molecule oriented in a particular direction, and here we have the angular momentum vector. So, we will now project this angular momentum vector on this z axis. So, if we project, what we need to do, we need to take this end of this angular momentum vector and draw a straight line, such that this straight line that we have drawn and the z axis makes an angle of 90 degrees. So, this yellow arrow is our angular momentum vector L, and the projection along the z axis is given by L z. So, depending on how the molecule is oriented, the value of L z can vary anywhere from the actual magnitude of L or angular momentum in the positive direction to the actual magnitude of angular momentum L in the negative direction if we rotate the diatomic molecule all the way around. However, the molecule cannot arbitrarily orient itself with respect to the laboratory reference axis or the z axis, but the molecule can orient itself only in certain directions. In other words, the number of different directions which an angular momentum vector L may take up is limited. The orientation is also quantized. The component of angular momentum along a given reference direction, say along this z direction, is given by the quantum number m j. So, we can see by the way we have projected that L z equals L cos theta, where theta is the angle formed by the z axis and the angular momentum vector, and we can write this as root over j times j plus 1 cos theta. So, for integral values of the rotational quantum number j, the angular momentum vector can only take up directions such that this m j is 0 or an integral multiple of angular momentum units h cross. So, this puts a restriction on the angular momentum vector. So, we can write L cos theta equals root over j times j plus 1 cos theta equals m j h cross. And in other words, we can write cos theta equals m j divided by root over j times j plus 1 in quantized angular momentum units. So, we have cos theta equals m j divided by j times root over j plus 1. We know that minus 1 is less than equal to cos theta less than equal to 1. So, it can be shown that as the maximum and minimum value of cos theta is 1 and minus 1 respectively, m j can take values. So, the values that m j that can take are from minus j to plus j, which also includes the value of 0. In other words, the possible number of orientations is 2 j plus 1, because from minus j to minus 1 we have j values, and from plus 1 to plus j we have j values, and we have one another value, that is 0. So, we have j in the negative side, j in the positive side, plus 0, which gives 2 j plus 1. So, now we have to know how we get this extreme or the minimum value of m j as minus j and the maximum value of m j as j for a level associated with rotational quantum number j. So, let us assume m j equals j. So, we can write cos theta equals m j by root over j times j plus 1, and because m j equals j, we can write this is j by root over j times j plus 1. So, we can write j as root over j times j divided by root over j times j plus 1. So, this becomes root over j by j plus 1. So, as j is less than j plus 1, root over j by j plus 1 is less than 1. So, for this case we have cos theta is less than 1. So, this is permissible. So, j can be one value of m j. Now, let us increase the value of m j by 1 unit. So, let us say m j equals j plus 1. So, let m j equals j plus 1. So, cos theta becomes m j by root over j times j plus 1, that is j plus 1 divided by root over j times j plus 1. So, we can write this as root over j plus 1 times j plus 1 in the numerator and j times j plus 1 in the denominator. If we cancel out j plus 1, j plus 1, we get root over j plus 1 divided by j. So, now because j plus 1 is greater than j, for this particular case we have cos theta is greater than 1, but we know the limit of cos theta. So, this value of m j is not permissible, because cos theta cannot be greater than 1. So, the maximum value of m j is j. Now, let us look into the minimum value. So, let us assume m j equals minus j. So, we can write cos theta equals minus j times root over j times j plus 1. So, this we can write as minus root over j times j divided by root over j times j plus 1. So, this becomes minus root over. So, we cancel j and j in the numerator and the denominator. So, what we get is root over j by j plus 1, and because we have a negative sign and within the square root we have a number that is less than 1. So, we can say cos theta is greater than minus 1. So, this is again a permissible value. So, m j can take a value of minus j. However, if we put m j equals minus of j plus 1, then cos theta becomes minus of root over j plus 1 times j plus 1 divided by j times j plus 1. So, it becomes minus of root over j plus 1 by j. So, we have a number which is greater than 1, the square root of that number is also greater than 1 and we have a negative sign. So, in this case cos theta is less than minus 1, which is not permissible. So, this cannot happen. In other words, m j cannot be minus of j plus 1. So, we saw the maximum value of m j is plus j and the minimum value of m j is minus j. So, that is how we can say that m j can take up these values from minus j to plus j, which actually tells us there are 2 j plus 1 different orientations. In other words, each energy level is 2 j plus 1 fold degenerate. So, what does this result imply? This implies that the angular momentum vector cannot be perfectly aligned to that arbitrary laboratory axis or the z axis. This is because L is given by root over j times j plus 1 h cross, but L z, the absolute maximum value that L z can have is j times h cross, which is root over j times j times h cross. So, we can see that L is always slightly greater than L z. So, let us take the case of j equals 1. So, because j equals 1, the value of L is root over j times j plus 1 h cross, that is root over 1 times 1 plus 1 h cross, that is root over 2 h cross. Thus, the angular momentum vector of magnitude root 2. So, root 2 is the magnitude. So, this vector with magnitude root 2 can have only 3 values of m j, because j equals 1, m j can be minus 1, 0 and 1. So, let us take the diatomic molecule and which is initially oriented in that vertical direction, which is our z axis. So, let the reference direction, that is the z axis, is along the molecule. So, the L or the angular momentum vector is oriented perpendicular to the molecule and the value of L or the magnitude of L is root 2. Now, if this molecule reorients, so let us say the diatomic molecule reorients this way. So, we have a new direction for the angular momentum vector L, the magnitude is still root 2, but if we take the projection has to be either plus 1 or for a different kind of rotation the projection has to be minus 1. So, all 3 directions have the same angular momentum, that is L or root 2, and thus for j equals 1 it is 2 j plus 1, that is 2 times 1 plus 1, that is 3-fold degenerate. So, now let us look into j equals 2. For j equals 2, m j can take values of plus 2, plus 1, 0, minus 1 and minus 2. So, which makes that j equals 2 is 5-fold degenerate. The reason we have two quantum numbers in this problem, one is j, the rotational quantum number, and the other is m j, because in order to define the position of a particle on a sphere, we need theta and phi. So, in the last lecture, when we are talking about the selection rules, we made this transformation from Cartesian axis to this polar coordinates. So, or we made this transformation from x, y, z to r, theta, phi. So, when I am talking about this theta and phi, I am talking about this theta and phi, which we mentioned in the last lecture. So, there is a boundary condition associated with both of these coordinates theta and phi, and so there is a quantum number associated with each of these boundary conditions. So, the issue of spatial degeneracy is complex. So, here you see two different representations of spatial degeneracy. See, on the left, the j vector is projected on the z axis. So, when j equals 2, there are 5 possible values of m j, that is plus 2, plus 1, 0, minus 1 and minus 2. So, on the right we see the 5 cones that are being swept out to represent the angular momentum vector. The angular momentum vector can lie anywhere on the surface of the cone for a particular value of m j, and when I draw this, I have the value of m j for this particular cone is plus 2. So, the rotational energy depends on j, the rotational quantum number, but does not depend on m j. It does not matter what the orientation of the rotational axis is with respect to the laboratory. In other words, a particular direction is not more important than another, or in terms of rotation, no direction is easier to rotate than the other. The importance of the spatial orientation is the existence of the spatial degeneracy. In one molecule, let us say the molecule is in the jth quantum state, there are 2 j plus 1 possible orientations, which all have the same rotational energy, and this is the definition of degeneracy. So, for j equals 2, because the molecule can be in 5 quantum states, it means we have 5 energy states, and all these 5 energy states have the same energy, that is they are all degenerate. So, if we take j equals 0, the only possible value of m j is 0. That means, there for j equals 0, it is not degenerate. For j equals 1, m j can take values of minus 1, 0 and 1. So, the degeneracy of j equals 1 is given by 3, or it is 3-fold degenerate. For j equals 2, m j can take values from -2, -1, 0, 1, 2. So, the degeneracy for j equals 2 is 5. For j equals 3, m j can take values of -3, -2, -1, 0, 1, 2, 3, or the degeneracy for j equals 3 equals 7. Or for any level j, the degeneracy is given by 2 j plus 1. So, we see that for j equals 3, 2 j plus 1 equals 2 times 3 plus 1, that is 7. So, we can see in terms of the diagrams, energy level diagrams, let us say j equals 0, j equals 1, j equals 2, j equals 3. So, j equals 0 is non-degenerate. So, we can think j equals 1, there are 3 levels of equal energy. So, g j equals 1 equals 3, j equals 2, we have 5 levels of equal energy. So, g of j equals 2 is 5, and for j equals 3, we can think there are 7 levels of equal energy. So, g of j equals 3 is 7. So, we can say in general for j equals j, degeneracy g j is 2 j plus 1 fold degenerate. Now, let us look into a couple of problems regarding degeneracy. The first problem we have is the energy level is given by 20 B wave numbers. What is the degeneracy of the level? So, we know the energy of any level j is given by B j times j plus 1. This is the nu bar j. So, here we have B j times j plus 1 equals 20 B. So, we have j times j plus 1 equals 20, or j squared plus j equals 20. So, we can write j squared plus j minus 20 equals 0, or I can further write j squared plus 5 j minus 4 j minus 20 equals 0. That means, j if I take common, j plus 5 minus if I take 4 common, j plus 5 equals 0, or in other words j plus 5 and j minus 4 equals 0. So, the values that j can take is minus 5 and plus 4, but j cannot be negative. So, j cannot be minus 5. So, j equals plus 4. So, if j equals plus 4, we know the degeneracy g of j is given by 2 j plus 1. So, that is 2 times 4 plus 1, that is 9. So, in other words, because this is a multiple choice question, the correct answer is C. That means, the degeneracy of the level is 9. So, now we have another question, the degeneracy of a certain rotational level j double prime is 15. So, here in the last problem we calculated the degeneracy. In this problem the degeneracy is given. So, if transition happens from j double prime to j double prime plus 1, this transition corresponds to, so we have 4 options, we have to choose one. So, because degeneracy is 15, we can write 2 j plus 1 equals 15, and because we are talking about a particular level which is j double prime, we will write 2 j double prime plus 1 equals 15. So, j double prime equals 15 minus 1 divided by 2 equals 14 by 2 equals 7. So, we are talking now about a transition that happens from j double prime to j double prime plus 1, that is the transition is from 7 to 8. So, the energy for this transition should be delta nu bar j, that is given by 2 b times j double prime plus 1. So, that is 2 b times 7 plus 1. So, that is 2 b times 8, that is 16 b. So, the correct answer out of all these choices is D, that is 16 b.